Okay, to quickly summarize what we were supposed to finish in class was critical angle, to finish these critical angle notes. What we saw on the simulator was that if you're going from a more dense medium to a less dense medium, the wave is speeding up, and so it's getting closer to this boundary line, and there comes an angle at which, boom, the refracted light is gone, and all of the light is reflected. This does not happen if you're going from less dense medium. If I flip these around, if I go from air to glass, rather, that never happens. You can go from 0 to 90, well, to 89.9, and you'll always have some refracted light, right? It's just some, because it slows down and it drops down. It never quite gets high enough. But when you go from a more dense medium to a less dense medium, so 1.5 to 1, you get this. And what we're looking for is the critical angle. Now, the critical angle is the smallest angle of, of incidence that has no angle of refraction, okay, where all of the light is reflected. And so that is what we're looking for. We find this, and we call this the critical angle, okay? And we do this by determining when theta r is not 0, but 90 degrees. Madison nicely pointed that out. It's 90 degrees. That's what we set it to. Because if we look at this, when there is refraction, it's 49.2. I can make it bigger or smaller, but it's going to be somewhere between 0 and 90 is the max, right? But once it's 90, then it no longer refracts and it all reflects, okay? And anything greater than 90, well, this would refract more than 90. No, it's not going to do that. It's just going to reflect. And so we can find the critical angle if we set theta r, that is the angle of refraction. So that is this angle. If we figure out when is this angle 90, that is the critical angle. Okay, so what is the critical angle for a light wave from water to air? Okay, and so this is from water to air. So we're looking for this. We can use the simulator and predict that it's about 48.7, but let's do the math. Okay, so the way that we do this is we're going to do, we're looking for the critical angle, and so that is the angle of incidence. Okay, that is our question. And what do we know is this. We know that theta r is 90 degrees. When theta r is 90 degrees, that is when this is the critical angle. Okay, that is when it starts to just reflect and not refract. And so what else do we know? Well, we actually know a lot. We know that the angle of incidence, sorry, the index of refraction for the incident is water, okay? Because we're going from water to air, and water has an index of refraction of 1.33, so that's the incident index of refraction, and the refracted index of refraction is air, which is 1.00. And so now we can set up our equation. So what we're going to do is we always put theta I on top, so it's going to be sine theta I over our sine theta r, which in this case is 90. Now, if you punch sine 90 in your calculator, you actually get 1. Now, that's awesome because we can ignore that 1 because anything divided by 1 is just whatever it was. Dividing by 1 doesn't change anything. And so this is good. And then we do nr over ni, right? So nr is 1.00. How can we do nr over ni? Because that's how the formula is. If sine theta I is on top, then the formula has nr on top. And so, and it should be like this. And what you'll see is this only works when the smaller number is on top. So it has to be going from a more dense to a less dense. And so what we get then is theta I equals inverse sine, so sine negative 1, of our 1 over 1.33. Okay, you punch that in your calculator, and what do you get? So grab my calculator here. Inverse sine of 1 over 1.33. We get 48.8 degrees. Hey, look at that. Isn't that what we predicted? 48.7, 48.8. Boom. We nailed it. All right. And that simulation nailed it because it's using the same formulas that we're using. So that's no surprise. And so that's how we do it. This step is a bit of a stretch. If it is, then let's go. Then tell me, and we'll go over it in class. But hopefully, this is okay. The sine 90 was 1, and so what we did is we just did the inverse sine of whatever is on this side. So this would be some decimal, and we do inverse sine of that. Okay, that's how we solve for theta. And so if we think of this question, Ian did a great job of understanding this and sharing it with the class. And if you were listening, then you would have heard his explanation, which was perfect. Who would see who if this is the case? Well, it'd be easy to think, oh, remember, through this guy can see because light going from him would go straight through to this guy. But wait a minute, the light from the sun, right? The sun is up here, the screen sun, would go and it would hit this guy, bounce off his face, and come this way. And this light would go right through to the scuba diver's eyes, and the scuba diver would see him. Okay. Now, alternatively, what would happen to the light from that goes from the sun and bounces off this guy's mask? It would come up here, and it is greater. 61 is bigger than the angle of refraction, this critical angle. So all of the light is going to bounce down here, and this guy is going to see nothing. And so that is super cool to think about. All right. The last question here is between quartz and glass. Where does the critical angle exist, and what is it? Okay. For this, you need to look at the back of your formula sheet. Okay, and you'll get the index of the incident index of refraction and the refracted index of refraction. Now, I don't even know off the top of my head. I don't have the formula sheet, so I'm going to pause the video and get that stuff. But what I think is I'm just going to give you the answer, and I want you to try to get there, okay? And so you got to decide, it's got to go from the more dense, whichever is more dense, to the less dense, okay? And then you just set up your equation just like this. It's going to be the same thing. It's going to be sine theta I of the less dense divided by the more dense, okay? So this is always, when you're looking for critical angle, when you're looking for CA, critical angle, it's always going to be sine theta I equals the n of the larger n. How do I write that? Oh, it should be smaller n, not larger. The smaller n divided by the larger n. All right, this is always how you set it up because we're always dividing by sine 90, which is just 1. And so we can kind of ignore that piece. We can kind of ignore this stuff and just do sine theta I is smaller n divided by larger n. All right, I'm just going to end it there. I think you can figure out that one. I'll pause the video. Oh, okay, I'll do this. I'll pause the video. I'll put up the answer, but I want you to do the work. See if you get the same answer. So here's the answer. We take sine theta I as 1.46. That is the quartz divided by the bigger one, which is the glass, which is 1.5. And so quartz ended up being NR. So I had these flipped around. And this ended up being NI because the incident has to be going from the more dense to the less dense, right? And so then we get, if you did it backwards, your calculator won't even let you get an error because you can never have you can't do it backwards. You can never have it. I won't do that too much, okay? You can never have a critical angle if it's from less dense to more dense. And so then our answer is 76.6 degrees. So we move the sign over by doing inverse sine of our fraction there, and that's what we get. That's it. All right. The rest of your time can be done doing the assignment.